Okay, let's start with chapter 6.5. We have to talk about the selection, the choice of the sampling time. In controller design, you have learned to design the Ks and the Ts, but now in digital controllers, there is a new question: how large should T sub O be? How large should be the sampling time, sampling frequency? I give you 5 points where you can check if your choice is good, but of course the choice stays free. There are 2 upper limits, the first points, and then 3 lower limits. Upper limit means you should make T sub O not too large. Lower limit means you also should select the sampling time not too small. So the first is a main point in digital systems, has something to do with the Shannon limit. Make some notes. Choice of sampling time. If sampling time is too large, changes of process output can not be detected. Let's have a quick look on the curves of the first lessons. If this is the output of the process and you sample, then of course, if your sampling time is too large, then changes of process output could not be measured with the ADC, and then the controller cannot react. So you should cover changes as fast as possible. In signal theory, in digital signal systems, it is easy. You can know the Shannon theorem, look for the highest signal frequency, then double this, and then you have a good minimum sampling frequency of your digital system. This works in signal theory, but in control systems, we have no signals. We have process output values, but how large is the frequency of this signal? You don't know it, because normally these are constant or slow changing values. The idea what I can use is the following. Let's look on fast changes of output. How fast could an output of a process change? Let's look for a very simple block. And the fastest change can you get if you have the fastest change of the input. And the fastest change of an input is a step. So we assume a step function at the input and then check how fast is the output changing. Depends on the process. Let's assume a very simple process. The most simple process in control theory for typical systems is a PT1. Yeah, and the fast change at the input can produce a change in the output. If this is Y, output signal, then the fast change of the output gives the step response of a PT1. So depending on the time constant of your system, if you have a PT1, you know the time constant is responsible for the speed of change. If sampling time is very small, if process time constant is very small, this goes fast. If process time constant is slow, this takes a while. So the process time constant is a good indicator for the speed of output change. And that is what I want to show you. We know after one time constant. I wiped it out and redraw it with one curve after one time constant. You know, in the typical exponential function output of my PT1 system, if this is k, the point at one process time constant is 63% of k. So now try to follow me if I say, if I sample at this point and I have 0, and I sample after one process time constant at this point, then the output is changed with the measure of 63%. So the change is nearly complete, and I think that's really too late to react on the system. So a recommendation or an upper limit is take the process time constant as a measure, and a good thumb rule says, okay, if you cover this step response with 10 points, then this is a good fast system, you can react fast enough. Sampling time should be smaller than 0.1 process time constant. If you have a process which behaves like a PT1, T is known. If the process has more than one PT1, T is then largest process time constant. Or if you have several time constants which are really in the same range, or T is, sometimes people take the sum of all time constants of all PT1s. Then you make no big error. That is a good recommendation. So I think, if you select your sampling time 10 times smaller than the largest process time constant, then this is a good way. That's the first recommendation. There is a second recommendation which has something to do with PID design. This has to do with the effect that a digital system has a delay. So that's right, digital controller has a delay. We will discuss this point later. With delay time, depending on your approach, between 0.5 sampling time smaller than delay time, smaller than 1.5 sampling time. That is the result of discussions coming in some of the next chapters. So the worst case in your design is, the larger the delay, the bigger the problem. Is TD, we assume TD is 1.5 sampling time, the delay time. A delay has a phase shift, a negative phase shift. Has negative phase shift. The size was discussed in the Control System 1 lecture. You can look in old notes. I give you the result. The phase shift of a delay can be calculated depending on the delay time is negative. Delay has always negative phase shift depending on radian frequency multiplied with delay time. And in our discussions we very often use the degree value, so we have to multiply with the degree to radian conversion factor. and then you get the delay of a phase time, delay time block in degrees. Okay, remember that negative phase caused always problems or speed reductions in closed loop systems, or we can look back to a FRA design of an analog computer system, analog control system, FRA design. If you have done this, you know response. The response is in. You know the phase margin value. Phase margin is a kind of damping indicator, and crossover frequency. Crossover frequency. Yeah, look back in control system 1. These both values are known if you have made an FRA design. Phase margin is then reduced by the phase of the delay if you unchanged the design parameters. So we have the same control crossover frequency, then you reduce the delay of the phase margin with the delay of your delay time, delay phase of your delay time block. So delay reduces phase margin, and then it means damping. Gives caused by the delay reduced damping. And you see now a ratio, a relation between the reduced damping and your sampling time. The damping depends on the phase margin. The phase margin depends on the delay time phase. And the delay time phase relates to the delay time of the damping of our digital system, and this is proportional to your sampling time. If you put all things together and say, for example, if phase margin reduction should be in a not too large value, is smaller, say 5 degrees is good. If you have 60-degree phase margin, or 55 or 50 instead of 55, yeah, if you have a change of 5-degree phase margin, to get an acceptable design. So this is a limit for the damping reduction. Okay, can we now put all things together to get an limit equation for my sampling time? Yes, we can do. We put now all things together and get the following result. So we can say, okay, the phase of the delay time block, the magnitude should be smaller than 5 degrees. We ignore the sign, the negative sign. So we can say, okay, this should be smaller than omega delay time times 180 divided by pi. Now we discuss the phase margin. So the radian frequency is our value of the crossover frequency, and we now replace the delay time with our digital controller sampling time value, and we get the following expression. This is 1.5 sampling time times crossover frequency times 180 degrees divided by pi, and this should be smaller than 5 degrees. And we solve this to our sampling time, so we bring all other things on the right side. Sampling time should be then smaller than 5 degrees times pi divided by 1.5 times crossover frequency times 180 degrees. If we switch to our paper, then you see the resulting value, the pi divided by 1.5 divided by 180, and delta phi max is replaced with 5 degrees. All values together gives the number 0.05818. 0.05818 times 1 divided by crossover frequency. So take your crossover frequency value out of your controller design, multiply with this number, and then you have a good limit. Sampling time should be smaller than this value. So these are two upper limits. Now I give you 3 lower limit values. Sampling time.